Example of using Athena to solve a partial differential equation. In this case, where we have both changes in time and changes in distance down the reactor. And so what I've done is put in the commands that are going to look similar to other Athena programs, namely declaring the variables they're going to use as real, and then putting in the rate constant, the inlet concentration. So these are not the concentrations in the reactor at time equals 0, but these are the concentrations that are continuously flowing in the reactor. There's no B, there's only A flowing into reactor. And I've put in here the integration time. So instead of integrating to a time that I put in F12, instead I've put the time, I put in F12, and I'll show you the variable TF, and that way I can just change the time here when I want to do integration to a different value. And velocity is just a linear velocity, which is constant for this system through the reactor, and L is just the length of the reactor. So if we hit F12, then we see that what we've selected is mixed system with a diagonal matrix, and we'll see what that means. The solution history, so I'm going to make variable U1 equal to Ca, the concentration in the reactor, any location and any time, and U2 equal the concentration of B. I've checked the box so that I can write Ca and Cb in the equations. So what's different now is this other box shows up. There's no diffusion term for this calculation, so this doesn't need to be checked. The space domain, because it's going to plot, as you'll see, concentrations versus space, namely distance down the reactor. So the inlet to reactor, that's the left boundary, shows some boundary conditions. So that's a distance of 0, and the right boundary is a distance L. And the number of points means it's breaking the reactor up into a small number of disks, if you like, where it's solving. In this case, 85. It needs to be enough to get reasonable accuracy, and is using a finite difference scheme. So I'll click OK on these for now. So what I want to do is, if I hit F11, it asks for an initial conditions. So as I indicated, I have two variables, and U1 is going to be the concentration of A, U2 is the concentration of B. So in this case, initial conditions does not mean the inlet to the reactor. It means at the start, what's the concentration in the reactor. So for example, my inlet concentration, my feed concentration is 0.01 for A and 0 for B, but I could certainly start the reactor off where this is 0.004 and this is 0.004 also, right? But I could certainly start the reactor off without a simple condition like nothing of A and only B. I can basically start, this could be a function, exponential decay with distance, for example. All that it says is what are the concentrations in the reactor at the beginning. So the next step is to hit F11 again. Now it's going to ask me for the equations that I want to put into the reactor. So I define rate as K times Ca, so I don't have to retype it each time. And now F1, so in Athena's, it's worth writing what we're really solving in Athena. We're saying E1 times the derivative of U1 with respect to T equals F1. That's what we're solving in Athena, and of course, likewise for E2 and derivative V2, etc. So when I write F1, I'm saying what's the right side of the differential equation. In this case, the left side, E1 is going to be 1, and this derivative of U1 respect to time is the derivative of concentration respect to time at any given point in the reactor. So my mass balance. Basically have a rate expression minus kCa because A is disappearing. And then I have a flow term, velocity times the derivative of u1 with respect to x. So this is, if we look at our normal equations for a steady state reactor, we have the derivative of the molar flow rate with respect to x, or you could have the derivative of the, I should say, velocity times the concentration with respect to x is going to be equal to minus kCa. So in the partial differential equation, the transient balance, the left side is the derivative with respect to t. And now this notation on the right side, ux means the derivative of u1 with respect to x. And of course, so that means that the derivative of the concentration of A with respect to S is a partial derivative in this case. So those two equations, they're similar, but this new notation when we're dealing with the partial derivatives. If I hit F11 again, it's going to ask me for boundary conditions. So I've cut and pasted in the boundary conditions. So again, if we look at F12 to remember what we're doing in the case where we have two variables, the left boundary is 0, the right boundary is L. So left boundary means inlet to the reactor, the right boundary is the exit from the reactor. So the first statement says at the left boundary, I'm also going to want E1 to be equal to 0, as you'll see. So this makes the concentration, my feed concentration in the reactor 0.01. This makes the concentration of B 0. And so at the left boundary, that's what this means. Everywhere else, then F1 and F2 are just the equations I wrote here. And this command in F says we're finished with the boundary conditions. If I hit F11 again, now it's asking for the coefficient matrix. What's the value of E, E1, E2? So again, in the interest of time, I've cut and pasted the values. So the coefficient matrix says that at the left side, the inlet, E1 equals 0. So I tried to put an explanation here since E1 times F1 on the left side is this concentration difference. The left side of this equation is 0, which means the right side is 0, which means at the inlet, Ca is equal to Ca0. So Ca is equal to Ca0 because F1 times E1, which is always how the equations, F1 equals E1 times the derivative. E1 is 0, so therefore F1 is going to be 0 at the left side. It's 1 everywhere else, which means these equations that are written down here now apply everywhere else. And that's all we need to solve. I need, of course, to save. And so it should be ready to solve. So I can tell it to solve. I can look at the graph. And so notice that space means distance down the reactor, right? Our possible variables, time, concentration A, concentration B, but space means distance down the reactor. So it's solving for concentration of A and concentration of B as a function, distance down the reactor. So, for example, initially, we made a constant concentration in the reactor for B, and likewise for A. But we had boundary conditions that were different from what that constant concentration was. And those only 10 points are displayed here. I think it's 10, 1, 2. So things can certainly be, are more detailed than this. It's not like this line represents the actual behavior. If I look at a different time, then of course the concentration of A has changed because we're now feeding in this higher concentration. And so I can go to longer times, and eventually I should reach, if I put a long enough time in, I should reach a steady state. So I can certainly compare the last two, and they're pretty close. I'm almost at steady state. I can run for a longer time. I can certainly do the integration. If you remember what I set here was the T final is 25. And I can certainly change that number to integrate for a longer time. If we look at the concentration of B as a function of different times, click a few. So notice the short time, the blue curve, because we started out at 0.004, and with the boundary condition of this being 0. And of course now it's changing. So at different times, concentration because of reaction is increasing, and we can pick a number of times and ask it to graph so we can see the behavior. So see, the idea is at a given time, just freeze that time. Here's how the concentration in the reactor behaves. If I wait until a later time and again look at the concentration throughout the reactor, this is the concentration throughout the reactor at a time of 3.8 minutes in this case. And eventually it goes to a high value. This is for, say, a catalytic reaction, but the activity is not changing. And that's really all we need to solve these partial differential equations. We can certainly go in and change the properties so that we could make this a high concentration in the reactor. And so then that's going to change the behavior. And if we hit the graph button, and again we're going to plot versus space, which is distance down the reactor. And if I look at the concentration of B as a function of time, graph just a few values, you see the behavior looks different as I've changed that inlet concentration, short time, and then intermediate time, longer time, not what your intuition might tell you would be the behavior. We can look at more times to see what's happening. Not much is changing there. If we go to the shorter times, then we can see how the behavior is evolving. And it's really, more complicated. But the idea is we can solve now partial differential equations and watch as we approach steady state in this case. And as long as we integrate for long enough time, we'll reach a steady state value, which in this case for 25, it's probably pretty close to steady state.